Hello and welcome to another video. In this video we're going to be working on second minimum time to reach a destination. And here you have a graph with n vertices and you have some edges. And each vertex is a traffic signal which changes color from green to red every change minutes. And they all change at the same time. So like imagine these are all like traffic lights, they all change at the same time. And you're not allowed to travel if it's red. So you can get there if it's red, but you can't actually start going if it's red. And you want to return the second fastest time to get to the end from the start. Yeah, so you want to go from 1 to n and you want to get the second fastest time. So there's a couple things here. Let's look at the examples and then there's a couple things to recognize. And I think this problem's pretty difficult, to be honest. I think most graph problems aren't too bad. But this one's pretty difficult. It's not like super difficult, but definitely warrants a hard problem at least. Okay, so here they show you that the fastest path is this. And so here it takes 6 seconds for the fastest path because at time equals 3, you're over here. And then you can still go at time equals 3 because at 5, it changes to red. So time equals 3 is still green, so you just go and it's 6. And then the second fastest is this one. So at time equals 3, you're here. At time equals 6, you're here. But the light changes to red at 5. So every 5 seconds it changes. So like it'll be red at 5, then green at 10, then red at 15, and so on. So here we're here at 3, here we're at 6. Now we have to wait till 10 for it to change green again. And then from 10, we need another 3 seconds over here at 13. And that's the second fastest path. And then here, you basically so there's like the fastest path is just this, right, 1 to 2, and that is time 3. And you can also take a path where you just go there and then you come back and then you go there again, and that would be, so they let you do that. So basically you'd be here at time 3. Now this is going to be red, and then at time 4 it's green, and then here you're back here at 7. And at time 7, it's red at 2, it's green at 4, it's red at 6. So time 7, you have to wait again till 8, and then you're back here at 11. So hopefully that makes sense how the times work out. So basically, there's a couple things to recognize, and this is kind of like the constraints are kind of tough because like there's n 10 to the 4th nodes, and then a lot more edges as well. Like there's 10 to the 4th edges. No duplicate edges, and each vertex can be reached. So that's saying the whole thing is connected always, and they're undirected. So the first thing to recognize is if I have multiple paths with same number of edges I traversed, they will take the same time. This is like the first thing to recognize in this problem. So basically, if you go, let's just say I don't go to the end, but let's say I take a path like this path here, 3 edges. So I go from 2 to 4, it takes 3 edges. That will take the exact same amount of time, assuming I start at time 0 as like something like this, right? Because it doesn't really matter what your like actual route is, as long as you took the same number of edges, as long as the length of the path is the same, the time is going to be the same. So that's one. Secondly, less edges traversed will always be faster. And so I tried to find like a counterexample for this not being true, but it's basically always true. Because for every traversal, you either have to, you're always going to have to take time t, but then you'll also might have some waiting time. Have to wait. So that means that if you have n edges, right? So from number 1, if you have n edges that you took, if you take n plus 1 edges, the first n will be the same, and then for the last edge, you're going to add another either time or time and waiting time. So basically, the time doesn't really matter here. Like you can just take the time out of the equation and all of this, and you can just say like, give me the second shortest path from the start to the end. And the other thing that you have to look out for is, let's say we have an example like this. So something simple. Let's see. Yeah, okay. So let's say this is 1, this is 2, this is 3, this is 4. So we're trying to get from 1 to 4, right? We need to go like this. Yep. Okay. So here, these two paths, a path from 1 to 2 to 4, and 1 to 3 to 4, actually take the same exact amount of time, right? From this number 2, or from number 1. If I take the same number of edges to get to my path, which is just 2, they're gonna take the same amount. So here, like the shortest path will be one of these two, and you don't want to return the second. You want to make sure that your second shortest path actually takes more edges than this. So actually here, the second shortest path would probably be something like go from 1 to one of these, and then come back to 1, and then go back down. So it would actually take 4 edges, something like that. Or, you know, there's a bunch of other ones, right? There's like 1, 3, 4. 1, 3, 4, 3, 4. That would take 4, or 1, 3, 1, 2, 4, or anything. But basically, you want to make sure that your second shortest path actually takes more edges. So find shortest path. Make sure second shortest path is actually longer, right? So you might be able to get to the same destination through different paths that take the same amount of time. But it tells you, it doesn't say like, if you take all the paths, give me like, and the two, and there's paths with the same amount of time, then just return that, right? They specifically ask for the second minimum time. So AKA, you know, if the shortest path is like, I have to traverse 4 edges, I want a path that traverses more than 4 edges. Okay. So now that we know, all we're really concerned about is basically figuring out like, how many edges do we need to traverse in the second shortest path? And every edge, like I said, the time and all this is like irrelevant. We can calculate this later, or you can calculate this as you go. Doesn't really matter. But basically, this is basically the same as find the second shortest amount of edges I can traverse, where every edge has a weight of 1. So because every edge has a weight of 1, like one isn't faster than another, we can do some kind of BFS thing here. And so normally in BFS you have a couple things, right? You have like a queue, and you're traversing, and then you have like a visited set to make sure that like if I visited a node, I don't visit it again, because in a BFS, if every node has length 1, if something's in a queue, I don't want to put it in the queue again, because if I visit something, the first time I visit it is guaranteed the fastest way to visit it. So we have to do some slight modifications here. So instead of having a visited set, we will have a visited either array or a hash map. So we'll say array. And instead of that, we're going to have 2 distances that we have to visit this array. So we'll have like the fastest and then the second fastest. And we can just initialize both of these to like infinity or something. And then whenever we visit a node, we're going to check, have we visited it before? Like if this is infinity, we haven't visited it yet, right? So then we can just write down like how long that took. We're just going to record like either the number of nodes we traversed, or the number of edges we traversed, or the time. You can calculate the time as you go, or calculate the very end. Like given you traverse 5 edges, you can calculate the total time for that at the very end if you want to, or during your thing. So if our current time is less than fastest, then we will store this in fastest. And then we have another case where if our current time, and this is where we want to make sure that if we traverse, like if we take a path like this and a path like this, once we already got to 4 through a path like this, we don't want to record this path as well because they're equal. So we want to make sure if our current time is greater, so if 1 is true, we just store here. If our current time is greater than our fastest time, and we still haven't visited, and we still don't have a second fastest, then store there. And then by definition in a BFS, like if you visit a node a bunch of times, like the first time will be the fastest, the second time will be the second fastest, and so on, but there might be ties, right? Like I said, like if I visit 4, the first time will be through 2 edges, the second time will also be through 2 edges, and then if I keep going, but what I'm saying is like I wouldn't want to record here. So let's kind of walk through how this would look like. So basically, let's say this is our simple graph. So in the beginning, we're just going to say the fastest time to visit our starting node is just 0, because you just start there, right? So that's like the fast time. And then everything else we'll just make infinity. So we'll just say this infinity, this infinity. So the fastest time will be infinity, the second fastest time will be infinity. Yeah. Okay. And then we'll do some kind of like basic BFS with that. I'm probably not going to draw out the BFS, but let's say from 1, the first node we're going to visit is either 2 or 3, right? And we're going to say that took a time. I'm not going to write out the time. Instead, we'll just write out like the number of nodes we traverse. So actually, let's just say here, let's do it this way. So here, we're going to visit this node with 1 edge that we took, and then the second one will be infinity, so infinity or something. Then we're going to visit this one, right, in a BFS. Like this will be the second node visited. So this will take, the fastest will be 1, second one will be infinity. Then the next node we're going to visit, like because we're going to be at these 2 nodes, will either be 4 or back to 1. So let's say we visit 4 first. So this will be our fastest path. And we're going to visit it from one of these 2, doesn't matter really which one. So our fastest will be 2 edges, and then our second one's infinity. Then we'll visit 4 again from the other node, right? So our path will be like 1 to 2 to 4 or 1 to 3 to 4. But because we already have the fastest and our second fastest is 2 as well, we don't want to record that one. So then the other way you can go from these 2, because these 2 will be in our BFS, is basically, I guess I could show it here. So like from this node, these 2 nodes will be in our BFS, right? Then from these 2 nodes, we're going to go to this node and back here. And so here, once we go back here, this took 2 edges, right? Because we went here and here, or here and here, either one. So this will be 0 and 2 now. And if we visit this node ever again, we don't really care, because all we're going to record is this first and second fastest time, as long as there's not a tie. And anything more than that will be irrelevant, because those will never end up giving you the second best result. So that's the other thing to realize is, instead of storing if I visited a node or not, I'll just store the fastest time and the second fastest time. And anything else will, by definition, not give you the second fastest result, right? Because if I have some path that I've passed some node, if I passed it in the fastest time, that'll give me some answer. If I passed it in the second fastest time, that'll give me a smaller answer. And then anything less than that will give me an even smaller answer, and I don't care about that. So basically, yeah, now we're here. So we started here, we went to these 2 nodes, and then we went back out to here. So now from here, from this node, we can go back here, right? And that is 1, 2, 3. And it doesn't matter, like you go from this node or this node BFS, it doesn't matter which one you come from, it's still going to be 3. And this will be 3 as well. Okay. And then from these 2 nodes, once again, we can just go out to these 2. So we'll get a 4. And once we go out here, now we're never going to go out here again, because we already have the fastest and second fastest. So we're not concerned with any more time. So this basically disappears from our BFS. Now the only node that's in our BFS will be this one. And then we were going to, once again, go to the children and check, do we have a fastest and second fastest? Yes, we do. We have one for this, we have one for this. So this is all gone. So this will be in our like visited times or whatever. And then all we have to do is just return the second fastest time to visit node n-1 or node n, and that would be our answer. So this would be 4. So hopefully that makes sense. We're just gonna, instead of having a visited set, we'll just record the 2 fastest times to visit the node, and then our answer will always be the second fastest time to visit the last node. And we're just gonna do a simple BFS because if you take n number of edges, the time will be equivalent regardless of what path you take. And I'm going to calculate the time as we go. You can calculate it afterwards. Like you can figure out like what are the number of edges that I took to get here with this number here, and then you can calculate the time at the very end as well. Either one's fine. Okay, so let's take a look at the code. So first we're going to make a graph, and because this is a graph, so like I said before, in Java ideally you want to use arrays. So because everything's connected and you have 1 through n, we can just make a graph of 0 through n. We just won't use 0 to make it simple. Or you could do 0 to n minus 1 and then like change the index. So you'd have to take every number here and just subtract 1. Either one's fine. Or you can make a hash map if you want to for the graph. So basically, every single vertex will have a list of nodes it's connected to. You can't really use another array here because you don't know how many nodes it's connected to before you look at the edges. Okay, so we make that, and then for every edge, we just connect it, right? So we have our u, we have our v, and then we add u to v to u because it's bidirectional. Then we're going to make this like visited distance thing. And so every single node will have two values. The fastest amount of time it took to get there and the second fastest. And we're just going to initialize them both to infinity. And also, this should actually be this. So the fastest time to go from node 1 to node 1 will be 0. Because this is this example, right? Because you already start here. So like if you start here, the fastest time to get here is 1. And then what's the second fastest? Well, we might record it. And you do need that because like here we go from 1 to 2 to 1 to 2. But we're never going to do any more than that, right? So we're only going to revisit the first node at most once. But every other node we can visit at most twice. So then we make our queue. You can use a linked list or an array DAC, either one. And our initial thing is we have node 1 that we start at with a distance of 0. And so we just keep doing the BFS. We get the node and the time. And so from our current time to get to a node, so, oh yeah, I didn't talk about this, so let's talk about this. So let's say it changes every 5 seconds, and we have some current time like, I don't know, like 42 or something. This is our current time. So it changes every 5 seconds. And the time it takes, right, because there's a change and a time. And the time it takes, let's say, is 3 seconds. So to go from a node to another node, you're always going to take those 3 seconds, right? That always has to happen. But you might have to wait for a green light first. So if our current time is 42, we're always going to need to add the 3. But we also need to check how long we need to wait. And so to check how long we need to wait, it's pretty simple. Basically, the light goes... It starts at green and it goes green, red, right? So at 5, it'll be red. At 10, it'll be green. 5, it'll be red. 20, it'll be green, and so on. So to determine the color of the light, you can basically do your time divided by a floor divide, the change time, and you can figure out like how many iterations was this. So in this case, this would be 8. So because the light flipped 8 times and it starts at green, so it'll be green, red, green, red, green, red, green, red. So it'll be green right now. And how long has it, and if it's green, we can just go. Right, so if it's green, we'll just take our current time, we'll add 3 seconds and go. But let's say our current time is like 37. Then we'll do 37. And we'll get, can't count today, 7. That means the light's red. And how long has it been red? Well, that is just going to be 37 mod 5. So to figure out if it's red or green, just see how many, what your answer is. Is it odd or even? If it's odd, it will be red. If it's even, it'll be green. And to figure out how long it's been red or green, just take the mod, right? Because every 5 seconds it changes color. So it's been red for 2 seconds. So how long do we have to wait? We have to wait the change amount of time minus how long it's already been that thing. So those are kind of like the steps. First, figure out if it's red or green. If it's green, just add the time. If it's red, figure out how long it takes to be green, and then, yeah. So that's basically here. So we have this like cycle, and if there's an odd number of cycles, that means the light's red. So we have our current time, which is current time, and it will always need to add the time it takes to travel. But then we also have to figure out if it's red, then our wait time will be the amount it takes to change minus this like remainder. And then if it's red, then we need to add that as well. So now we have like our total amount of time to get to the next node. You could do this here, or like I said, you could at the very end do this for every single edge you traveled. Once you figured out like how many edges do I need for the second shortest, either one. Then we just go through our children and we check if our time to get to this node is less than the fastest time, which means, like I said, this just means it's infinity. So you can also rewrite this like this. So you can say if this equals integer max val, because like I said, you're guaranteed in a BFS to get to the first time you get there will be the fastest, second time will be the second fastest, third fast, and so on. But you can have ties, right? So if this is infinity, then this is the fastest time, and we're going to record it, and then we're going to put that into our BFS. Otherwise, just because like this, so we can say the same kind of thing. So we can do this. So just because the second fastest time is infinity, and the first fastest time is not, doesn't mean there isn't a tie, right? Because like in this example, you're gonna get to 4. The fastest path will be one of these, the second fastest path will be one of these, and they'll be identical, but you don't want to record both. So you want to make sure that the next time is bigger than the fastest, and the second one hasn't been like visited yet. So this is basically, has the fastest time been visited? No. Okay. And so yeah. And so this works as well. And then finally, at the very end, we're going to have this like distance visited array thing. And then the answer will just be the second fastest time to visit n. And so we can run that. And that should be fine. Yeah. So hopefully that makes sense. There were like a lot of assumptions you had to make. Hopefully they all make sense. If you have any questions about like, or not assumptions, but like a bunch of conclusions you had to draw, hopefully they make sense. If you have any questions, just let me know or something. And then let's go through the time and space. So yeah, it's basically just a BFS and like a more complex BFS. And that's usually what the hard problems end up being, is like, it's not just going to be like implement jigsters. It's going to be like implement 1 or 2 functions with modifications, because you actually understand how they work and like what modifications you need to make. Not just like I memorized BFS or jigsters or whatever. Okay. So first we make our graph, and yeah, so this is just like O of n or OV. So we'll just use vertices and edges, I guess, or like nodes and edges or something. So this is like node, this is edges. So yeah, this is just nodes. For every edge, we need to add it to the graph, so that's like E. Yeah. Then this distance thing is O of n, so V again, OV, OV. And then, so we basically visit every node twice. But we also go through the edges, and we go through the edges. Yeah, so I think typical BFS runtime is, I want to say V plus E. So we just do that twice, so it'll still be V plus E. So basically, we're only going to do like this for every node at most twice. So we'll visit every edge, worst case scenario, at most twice, and then every node at most twice. So I think that's just the same. And then storing the queue. So in the queue, we're going to be storing nodes and a distance, and we're only going to have a node in the queue at most twice. So I talked about that already. Yeah, so I think this is just this, where vertices plus edges or n plus length edges, one of those. Yeah. Then the calculating this time is constant time, so. Okay, and then space. So our graph is O of V. And then also we have nodes and edges, so it'll be like V plus E, I guess. And then our Q will have nodes, so that's OV. Our distance is OV. Yeah, so it's just, this is pretty common for graph problems, V plus E or like V plus E squared or something. Yeah. And then once again, if you look at like these solution runtimes, it's probably just going to be all array, or like, okay, so they use a deck and an array. And then if you look at the slower stuff, it's probably going to be the hash maps. So ideally, hash map priority queue, yeah. So you want to, if you want like good runtimes on LeetCode, I guess for Java, once again, you want to ideally use as many static arrays as possible. Here it's not possible, so yeah, I think they use an array list and a deck. So yeah, kind of same thing. Deck, linked list, array deck, whatever. Yeah, so kind of a long one. Definitely a lot of things you have to realize for this problem. Kind of a difficult one. So hopefully that was helpful. If it was, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.